Hello, everyone, and welcome to another exciting deep dive. Today, we're tackling a topic that is truly the backbone of chemistry, chemical bonding and molecular structures.
Yes, absolutely.
This isn't just theory, it's the fundamental concept that explains why chemicals behave the way they do, why reactions happen, and why every substance has its unique properties.
It really is foundational.
For all of you preparing for your Class 11th board exams, and especially those aiming for JEE, that's JEE or NEET, mastering this chapter isn't just important, it's absolutely critical for success.
I couldn't agree more.
I'm really looking forward to unpacking these foundational ideas with our expert tutor today.
Namaste, and I completely agree. Chemical bonding is indeed at the very heart of understanding chemistry. Think about it. Every day, scientists discover new compounds.
Whoa.
To make sense of this vast chemical universe, we need theories that explain fundamental observations. Chemical bonding provides that framework. It helps us understand why atoms combine, why only certain combinations are possible, and, crucially, why molecules always take on specific, predictable shapes.
Shapes are key, aren't they?
Definitely. So our mission in this deep dive is to systematically explore the major theories of chemical bonding and molecular structure. We'll ensure every concept is crystal clear and, most importantly, exam ready for you.
Perfect.
We'll cover the classic Kössel-Lewis approach, then move into the valence shell electron pair repulsion, or VSEPR theory.
VSEPR. Okay.
Followed by valence bond, or VB theory, and finally, the powerful molecular orbital, or MO theory.
That's quite a lineup.
It is. And always remember, at its core, bonding is nature's elegant way of lowering energy to achieve greater stability. It's like atoms looking for their most comfortable low-energy state.
That's a great way to put it. So let's start at the beginning. The Kössel-Lewis approach. Where did this fundamental idea come from, and how did it initially shape our understanding of chemical bonds?
Excellent question. The foundation of modern chemical bonding theory was truly laid back in 1916. Two brilliant minds, G.N. Lewis and Walter Kössel, working independently, mind you, provided a remarkably logical and, well, satisfying explanation for valence.
Independently, wow.
Yes. And what made their insights so groundbreaking was that they based their ideas on something seemingly simple: the remarkable inertness and inherent stability of noble gases.
Ah, like neon and argon. The ones that don't react.
Precisely. Imagine elements like neon or argon. They almost never react. This inertness, this lack of reactivity was the big clue.
So their non-reactivity was the key to unlocking the puzzle.
Exactly. Lewis especially gave us a very intuitive picture of the atom. He imagined a positively charged kernel, which basically includes the nucleus and all the inner non-valence electrons of an atom.
Okay, the core part.
Right. Surrounding this kernel, he proposed an outer shell that could hold a maximum of 8 electrons. He even had this clever visual analogy. He suggested these 8 electrons occupy the corners of a cube surrounding the kernel.
A cube.
Yeah, it was a model. So for an element like sodium, which has just 1 electron in its outermost shell, that electron would sit in one corner of this conceptual cube. But for a noble gas, all 8 corners would be completely occupied.
Filled up.
Exactly. This arrangement of 8 electrons, which Lewis termed an octet, was seen as a particularly stable electronic configuration.
And this octet was what every atom aspired to achieve, right? To become stable like the noble gases.
You've got it. Lewis's central postulate was that atoms form chemical bonds to achieve this stable octet. This could happen in one of 2 fundamental ways.
Okay.
Either through the complete transfer of electrons from one atom to another, which gives us ionic bonds.
Like giving away electrons.
Right. Or by the sharing of a pair of electrons between atoms, leading to covalent bonds.
Like teamwork.
Exactly like teamwork.
Mm-hmm.
In both scenarios, the ultimate goal for each participating atom is to attain that stable outer shell octet of electrons.
And how did Lewis make this electron tracking visible? Especially for us students learning to draw structures for exams. That sounds important.
That's where Lewis symbols become incredibly useful. G.N. Lewis introduced these simple notations specifically to represent only the valence electrons, the electrons in the outermost shell, because these are the ones actively involved in chemical combination.
So just the outer ones matter for bonding?
Generally, yes. The inner shell electrons are usually not involved. The beauty of these symbols is their simplicity. The number of dots placed around the chemical symbol of an element directly shows how many valence electrons it has.
Okay, so dots equal valence electrons.
Correct. This count helps us quickly figure out an element's common or group valence. It's either equal to the number of dots, or if the dots are more than 4, then it's usually 8 minus the number of dots. This is a quick way to predict how many bonds an atom might form.
Very handy. So Lewis gave us the octet and covalent bonding. What about Kössel's specific contribution? You mentioned him too. Was his focus on ionic bonding?
Spot on. Kössel's work, also in 1916, specifically zeroed in on ionic bonding. He made some key observations about the periodic table. Well, he noticed that the highly electronegative halogens, like fluorine and chlorine, and the highly electropositive alkali metals, like sodium and potassium, are always positioned very close to the noble gases in the table.
Ah, neighbors to the stable guys.
Exactly. And this wasn't just a coincidence. He noted that when halogens form negative ions by gaining an electron and alkali metals form positive ions by losing an electron, both processes lead the resulting ions to achieve the stable electron configuration of a noble gas.
So it's like they're trying to become noble gases themselves electronically.
Precisely. That's the core idea. The crucial point Kössel highlighted was that these ions attain either a stable octet, like NSM-pole configuration, or, for very small atoms like lithium, a duplet, like helium's configuration. This drive to achieve a noble gas configuration is a key reason for atoms to combine.
Makes sense.
Once these oppositely charged ions are formed, they are then powerfully stabilized by strong electrostatic attraction, forming the ionic bond.
Can you walk us through an example, maybe something common, like how table salt NaCl forms? That might help solidify it.
Absolutely. Let's take sodium chloride, NaCl. Sodium Na has 1 valence electron. Its configuration is neon, 3 cities. Chlorine, Cl, has 7 valence electrons, configuration neon, 3 center, 3 base, so it's just 1 electron short of an octet.
Okay.
Step 1. The sodium atom readily loses its single 3's electron. It becomes a positively charged sodium ion, No. This NaU ion now has the stable electron configuration of neon, a full outer shell.
So Na becomes Na plus Xe. Easy enough.
Step 2. That electron lost by sodium is then gained by a chlorine atom. This forms a negatively charged chloride ion, Cleo. The Cleon now has the stable electron configuration of argon, a complete octet.
And Cl becomes Cl now.
Got it. Step 3. Finally, these oppositely charged ions, Now and Clo, are powerfully attracted to each other through electrostatic forces. Think magnets. This attraction forms the ionic compound NeCl. The bond formed from this electrostatic attraction is called an electrovalent bond. And the electrovalence of an element is simply the number of unit charges on the ion it forms. For example, calcium forms Ca, so its electrovalence is +2. Chlorine forms Clo, so its electrovalence is Nash1.
That clarifies ionic bonding well. Now let's circle back to that octet rule. You said Lewis and Kössel developed it. Can you formally define it?
Certainly. The octet rule states that atoms tend to combine, either by transferring or sharing valence electrons, in such a way that each atom achieves an outer shell containing 8 electrons, the octet.
8 is the magic number.
Yep.
And the sharing part leads to covalent bonds, right?
Exactly. Langmuir, building on Lewis's work around 1919, refined the idea and really introduced the term covalent bond. He moved away from the static cube idea.
Okay. How does sharing work, say, for something simple like a chlorine molecule, Collier?
Good example. A chlorine atom, Cl, has the configuration neon 3 Salis or 3-apone. It has 7 valence electrons, so it's 1 electron short of the stable argon configuration. So if 2 chlorine atoms come together, each can contribute 1 electron to form a shared pair. This shared pair effectively belongs to both atoms. By sharing this pair, each chlorine atom can now count 8 electrons in its valence shell, achieving the stable octet.
Ah, so they both get to 8 by sharing.
Precisely. And we represent this using Lewis dot structures. You draw dots for valence electrons. A shared pair of electrons between 2 atoms is shown as a line, representing a single covalent bond, ClCl.
Can atoms share more than one pair, like double or triple bonds?
Yes, absolutely. That leads to multiple bonds, double bond. Atoms share 2 pairs of electrons, 4 electrons total. For example, in carbon dioxide, CO, carbon shares 2 pairs with each oxygen atom, OC-OC. A thiourea has a carbon-carbon double bond, CSC, triple bond. Atoms share 3 pairs of electrons, 6 electrons total. Nitrogen gas, N, is a classic example, with a triple bond between the two nitrogen atoms. N, ethene, a CO, has carbon-carbon triple bond.
Okay, that makes sense. Now, drawing these Lewis structures seems really important for exams. Is there a step-by-step way to do it reliably?
Yes, there is a systematic procedure, and practicing this is crucial. Here's how you generally approach writing Lewis structures for molecules or ions.
Count total valence electrons. Sum up the valence electrons of all the atoms involved. For example, in methane, CH0. Carbon has 4, each hydrogen has 1, so 4 plus 4, 1 equaled 8 total valence electrons.
Okay, just add them up.
Step 2. Adjust for ions. If it's an anion, negative charge, add 1 electron for each negative charge. For the carbonate ion, coson, you'd add 2 electrons. If it's a cation, positive charge, subtract 1 electron for each positive charge. For the ammonium ion, NH here, you'd subtract 1 electron.
Right, charge matters.
Step 3. Determine the skeletal structure. Arrange the atoms. Usually the least electronegative atom goes in the center, except hydrogen, which is always terminal. For example, in NF0, nitrogen is central. In COS, carbon is central.
Okay, central atom identified.
Step 4. Form single bonds. Place one shared electron pair, a single bond represented by a line, between the central atom and each surrounding atom. Subtract these bonding electrons from your total count.
Connect everything first.
Step 5. Distribute remaining electrons. Use the remaining electrons to complete the octets of the terminal atoms first, usually by adding lone pairs of dots. Then, if any electrons are left, place them on the central atom. Remember, hydrogen only needs a duplet, 2 electrons.
Build the outside, then the inside.
Step 6. Check central atom octet. If the central atom doesn't have an octet yet, you need to form multiple bonds. Convert lone pairs from terminal atoms into additional shared pairs, double or triple bonds, with the central atom until it achieves its octet.
Okay, use lone pairs to make double, triple bonds if needed.
Let's try a worked example. Say the CO molecule, carbon monoxide.
Okay, CO.
Step 1. Valence electrons. Carbon has 4, oxygen has 6, total equals 10 electrons.
Right, 10.
Step 2. No charge adjustment needed. Step 3. Skeletal structure is just CO. Step 4. Form a single bond.
CO.
Use 2 electrons. Remaining equals 8 electrons.
8 left?
Step 5. Distribute remaining electrons. Let's try completing oxygen's octet first. It's more electronegative. Give oxygen 3 lone pairs, 6 electrons. Remaining equals 2 electrons. Put these on carbon as a lone pair.
So O has 8, C has 2 from the bond plus 2 lone pair equals 4. Not an octet.
Exactly. Carbon only has 4 electrons around it. Step 6. We need multiple bonds. Let's move 1 lone pair from oxygen to form a double bond. CO. Now O has 6, C has 6, still not there.
Okay, try again.
Move another lone pair from oxygen to form a triple bond. CO. Now let's count. Oxygen have 2 lone pair electrons plus 6 shared equals 8. Carbon has 2 lone pair electrons plus 6 shared equals 8. Both have octets.
Ah, so the triple bond is the answer for CO. That step-by-step process really helps.
It does. Practice is key. Shall we try another one? Maybe an ion like the nitrite ion, NO-Ur?
Yes, please. Ions can be tricky.
Okay, NO-Ur. Step 1. Valence electrons, nitrogen equal 5. Each oxygen 6, so 2 6 plus 1 plus 18 electrons.
18 electrons total.
Step 2. Done. Added for charge. Step 3. Skeletal structure. Nitrogen is less electronegative than oxygen, so ONO. Step 4. Single bonds, ONO. Used 4 electrons. Remaining, we've 14 electrons.
14 left.
Step 5. Complete octets on terminal oxygens. Each needs 6 more, 3 lone pairs. 2 6 equals 12 electrons used. Remaining 14, 12 equals 2 electrons. Put these remaining 2 on the central nitrogen as a lone pair.
Okay, so terminal O's have octets. Nitrogen has 4 from bonds plus 2 lone pair equals 6. Still not an octet for N.
Correct. Step 6. We need a multiple bond. Take a lone pair from one of the oxygen atoms, doesn't matter which one, and form a double bond with nitrogen. So you can have ONO or ONO.
Wait, so there are 2 possibilities.
Exactly. This is a perfect example leading into resonance. Both structures are valid Lewis structures for the nitrite ion. The actual structure is a hybrid of these 2. We'll discuss resonance more soon, but this process gets you the possible Lewis structures.
Okay, I see. That process is clear now. What about formal charge? What is that used for?
Good question. Formal charge is essentially an electron bookkeeping tool. It helps us determine which Lewis structure is likely the most stable or lowest in energy when multiple possibilities exist, like in resonance. It's not the real charge separation in a molecule, just a formal assignment.
So it's like accounting for electrons. How do we calculate it?
The formula is straightforward. For any atom in a Lewis structure, formal charge, Fc. Total valence electrons in the free atom. Total non-bonding lone pair electrons, 12. total bonding shared electrons.
Okay, valence electrons minus lone pair electrons minus half the bonding electrons.
Precisely. Let's apply this to the ozone molecule O to see how it works. A common Lewis structure for O is OO, with appropriate lone pairs to satisfy octets. Let's number the oxygens 1, 2, 3 from left to right. OO.
Oh, got it.
For O, left, double bonded. Valence electrons E6. Lone pair electrons E is 4. Bonding electrons E is 4. 2 from the double bond. FCN O 6 force 2, 12 force 2 equals SEGO 2 equals 0.
Okay, 0 on the first oxygen.
For OO central. Valence electrons equals 6. Lone pair electrons equal 2. Bonding electrons equal 6. 2 from double bond, 1 for single bond equals 3 pairs. FC on O is 6, 2. 12, 6, 2, 3, plus 1. Plus 1 on the central oxygen. For O, right, single bonded. Valence electrons equals 6. Lone pair electrons equals 6. Bonding electrons equal 2, 1 from the single bond. FC on O equals 2, equals 6, 6, 1 equals 1.
Minus 1 on the third oxygen. So the structure is O0, L plus 1, O1.
Exactly. That's the Lewis structure for O showing formal charges. The general guideline is that the Lewis structure with the smallest formal charges and where negative formal charges are on the more electronegative atoms is usually the lowest energy and most preferred structure.
That makes sense. It helps choose the best representation. Now, you mentioned earlier that the octet rule has limitations. Can we revisit those? It seems important not to apply it blindly.
Absolutely crucial. While the octet rule is a fantastic guideline, especially for second period elements, it's definitely not universal. You must know the exceptions for your exams. There are 3 main categories. First, the incomplete octet. The central atom just doesn't get to 8 electrons. This typically happens with elements that naturally have fewer than 4 valence electrons.
Like boron.
Exactly. Think of lithium in Li only has 2 electrons around it. Beryllium in BH, B has 4, or boron in BCl or BFO, boron only has 6. Aluminum chloride, LK, is another common example. Second, odd electron molecules. If the total number of valence electrons in a molecule is odd, it's mathematically impossible for all atoms to achieve an octet. There will always be one atom left with an unpaired electron. Classic examples are nitric oxide, NO, and nitrogen dioxide.
Okay, odd number means rule broken.
Pretty much. Third, and very important for elements beyond the second period, is the expanded octet. Elements in the third period and beyond, like phosphorus, sulfur, chlorine, xenon, have access to vacant d orbitals, like third orbitals. These d orbitals can participate in bonding, allowing the central atom to accommodate more than 8 valence electrons.
So they can hold more than 8.
Correct. Prime examples you need to know are phosphorus pentafluoride, PFU is where phosphorus has 10 electrons around it, sulfur hexafluoride, SF where sulfur has 12 electrons, and even sulfuric acid, H. Interestingly, sulfur can also obey the octet rule in molecules like SCLO. So its ability to expand depends on the bonding situation.
So it's more of a general guideline than a strict law. Are there any other conceptual drawbacks besides these exceptions?
Yes, a couple more points. The octet rule is fundamentally based on the idea that noble gases are inert. But we now know some noble gases, particularly xenon and krypton, do form compounds with highly electronegative elements like fluorine and oxygen, see HESKRS, XCO. The simple octet rule can't explain why these inert gases react.
Right. The rule's foundation is shaky there.
Also, a major limitation is that the Lewis concept and the octet rule tell us nothing about the shapes or geometries of molecules. It just shows connectivity, not the 3D arrangement. And finally, it doesn't explain the relative stability or energy of molecules, which is crucial for understanding chemical reactions.
That makes sense. The octet rule is a starting point, but we need more advanced theories for shapes and energy. Okay, so the Kössel-Lewis approach gave us the basics of bond formation. But going back to ionic compounds, what about their stability in the real world? They exist as solids, not just isolated ions.
That's a great bridge to the next point. While Kössel-Lewis explains how ions might form conceptually, transferring electrons to get noble gas configurations, the real-world stability of ionic compounds comes down to energy considerations, particularly in the solid state.
Okay.
The formation and stability of ionic compounds depend mainly on 2 factors. 1, how easily the positive and negative ions can be formed from their neutral atoms in the gaseous state. 2, the arrangement of these ions in the solid crystal lattice.
Can you elaborate on the energy changes involved in forming these ions? I remember ionization energy.
Yes, forming a positive ion. Ionization requires removing an electron, which always costs energy. This energy cost is the ionization enthalpy. It's always endothermic energy absorbed. Mg plus E requires energy.
Right, pulling an electron away takes effort.
Forming a negative ion, anion, involves adding an electron, And the energy change associated with this is the electron gain enthalpy. This can be exothermic energy release or endothermic energy absorbed, depending on the atom. Xg plus E neg can release or require energy.
Okay, so it varies for anions.
Correct. Generally, ionic bonds form most readily between elements with low ionization enthalpies, metals, which lose electrons easily, and elements with highly negative electron gain enthalpies, nonmetals like halogens, which gain electrons readily. That's why most ionic compounds are metal-nonmetal combinations.
But you mentioned NHUR earlier.
Yes, the ammonium ion, NHUR, is a notable exception. A common concation formed entirely from nonmetallic elements, but the general principle holds.
So, if forming the ions themselves sometimes costs energy overall, low, i.e. might not fully compensate for positive or low negative EGA, where does the huge stability of ionic solids come from?
This is the crucial point. In their solid state, ionic compounds don't exist as separate ion pairs. They form highly ordered three-dimensional arrays called crystal lattices. In this lattice, each cation is surrounded by several anions, and each anion by several cations, all held together by strong electrostatic Coulombic forces.
Like a repeating pattern, right?
Exactly. Think of the NaCl rock salt structure. Now, the sum of the energy needed to form the gaseous ions, ionization enthalpy plus electron gain enthalpy, might actually be positive, meaning it seems energetically unfavorable if we only consider isolated ions.
Okay.
But this energy cost is overwhelmingly compensated for by the large amount of energy released when these gaseous ions come together and arrange themselves into the stable crystal lattice structure. This released energy is the lattice enthalpy.
The lattice formation releases a lot of energy.
A huge amount. Let's take an example again. Ionization enthalpy for now is about plus 496 kilojmol. Electron gain enthalpy for CLJ-mol is about next to 349 kilojmol. The sum is plus 496,349 equals plus 147 kilojmol. This looks unfavorable.
Yeah, positive means energy needed.
But the lattice enthalpy of N-saltace and energy release when forming the lattice is about next of 788 kilojmol. The overall enthalpy change for forming solid NCla from solid Na and gaseous kilogero is highly negative because this lattice energy release, next to 788, far outweighs the cost of forming the ions, plus 147, plus energy to atomize Na and Solare.
Wow, that next in 788 is massive, so the stability comes mainly from the lattice.
Precisely. The overall stability of an ionic compound is primarily due to the large energy released during the formation of its crystal lattice, not just the achievement of octets and isolated gaseous ions.
So lattice enthalpy is basically the energy holding the crystal together. How is it formally defined?
Yes, that's a good way to think about it. Formally, the lattice enthalpy of an ionic solid is defined as the energy required to completely separate 1 mole of that solid ionic compound into its constituent ions in the gaseous state, infinitely far apart from each other.
Energy required to break it apart into gas ions?
Correct. So for NaCl, the lattice enthalpy is plus 788 kilojmol. Note the sign change. It's the energy input needed. It's a direct measure of the strength of the ionic bonding within the crystal. Calculating it theoretically is complex because it depends on the precise arrangement of ions and all the attractive and repulsive forces.
Okay, that clarifies the energetics of ionic compounds. Now, understanding stability is one thing, but how do we describe the bonds themselves in a more measurable, quantitative way? What exactly are bond parameters?
Good question. Bond parameters are measurable properties of bonds that help us describe and compare them quantitatively. These parameters include bond length, bond angle, bond enthalpy, bond order, and they are closely related to the overall properties of the compound. Let's look at each one.
Sounds good. Let's start with bond length.
Bond length is defined as the equilibrium distance between the nuclei of two bonded atoms in a molecule. Think of it as the average distance because atoms are always vibrating slightly.
How is it measured?
It's measured using techniques like X-ray diffraction, electron diffraction, and spectroscopic methods. You'll learn more about these in higher classes.
Okay. And related terms like covalent radius.
Yes. The covalent radius is essentially the contribution of an atom to the length of a covalent bond. It's defined as half the distance between the nuclei of two identical atoms bonded together in a molecule, like in CLUs. So the bond length between two different atoms, A and B, is approximately the sum of their covalent radii, RA plus RB.
What about the van der Waals radius? That sounds different.
It is different. The van der Waals radius represents the overall size of an atom, including its electron cloud, in a non-bonded situation. It's defined as half the distance between the nuclei of two identical non-bonded atoms in adjacent molecules in a solid. It's always larger than the covalent radius because the atoms are just touching, not overlapping to form a bond.
So covalent is for bonded atoms, van der Waals is for non-bonded contact. Got it. Next parameter.
Next up is bond angle. This is simply the angle formed between the orbitals containing bonding electron pairs around the central atom in a molecule or complex ion. It's usually expressed in degrees.
Why is it important?
It's crucial because it gives us information about the spatial arrangement of orbitals and therefore helps determine the overall shape of the molecule. For instance, the HOH bond angle in water is about 104.5 degrees, defining its bent shape.
Makes sense. Angle determines shape. What about bond enthalpy?
Bond enthalpy is a measure of the strength of a chemical bond. It's defined as the amount of energy required to break 1 mole of bonds of a particular type between two atoms in the gaseous state. The unit is typically kJ-molo.
Energy to break the bond in the gas phase.
Exactly. For example, breaking HH bond in Hg requires 435.8 kJ/mol. Breaking O bond in OJ requires 498 kJ/mol. Breaking N bond in Ag requires a huge 946.0 kJ.
Wow, the triple bond in N is incredibly strong.
It is. The key takeaway is, the larger the bond dissociation enthalpy, the stronger the chemical bond. For a heteronuclear bond like HCl and HClG, it's about 431.0 gamol.
So, for molecules with multiple identical bonds, like water, H curl with 2 OH bonds, is the energy to break the first OH bond the same as the energy to break the second one?
That's a very sharp question, and the answer is generally no. In polyatomic molecules, breaking successive identical bonds often requires different amounts of energy because the chemical environment changes after the first bond breaks.
Ah, okay. So how do we talk about the OH bond strength in water, then?
Good point. For H0, breaking the first OH bond, HOH plus OH, takes about 502 kilojmol. Breaking the second OH bond, OH plus O, takes about 427 kilojmol. See, they're different. Because of this, for polyatomic molecules, we often use the mean or average bond enthalpy. For water, the average OH bond enthalpy is 502 plus 427, 2 equals 464.5 kilojmol. This average value is what's usually listed in tables and used for comparisons.
Okay, average value for polyatomics, what's bond order?
In the simple Lewis description, bond order is just the number of chemical bonds between two atoms in a molecule. Hydrogen, HH, bond order weaks 1, single bond. Oxygen, low, bond order 2, double bond. Nitrogen, N, N, bond order 3, triple bond. Carbon monoxide, CO, CO, bond order 3. Simple enough. Is there a relationship between bond order, length, and enthalpy?
Yes, a very important correlation. As bond order increases, bond enthalpy generally increases. Bond gets stronger, and bond length generally decreases. Atoms are pulled closer together.
Higher order, stronger bond, shorter bond. Makes sense.
Also, an interesting point for exams, isoelectronic molecules or ions, those having the same total number of electrons, often have the same bond order. For example, N-Euro, CO, and NOO all have 14 electrons and a bond order of 3. F and O both have 18 electrons and a bond order of 1.
That's a useful trick. Now, what about situations where a single Lewis structure just doesn't seem right? Like the ozone example you mentioned with the nitrite ion? That's where resonance structures come in. Exactly. Resonance is a fundamental concept and often tested. Sometimes a single Lewis structure is simply inadequate to represent the actual molecule accurately. This also becomes apparent when experimental data, like measured bond lengths, contradict what a single Lewis structure would predict.
Like in ozone.
Ozone is the classic textbook example. If you draw the Lewis structure for ozone based on the octet rule, you'll likely end up with one OO single bond and one OO double bond, like OO with formal charges and lone pairs.
Right. That applies one shorter bond, the double, and one longer bond, the single.
Precisely. But experiments clearly show that both oxygen bond lengths in the OO molecule are identical, around 128 picometers. This experimental length is intermediate between a typical OO single bond length around 1:48 p.m. and a typical OO double bond length around 1:21 p.m. Neither of the simple Lewis structures we can draw correctly explains this experimental fact.
So if one structure isn't enough, how do we represent a reality?
This is exactly why the concept of resonance was developed. When a single Lewis structure is insufficient, we represent the molecule using multiple contributing structures, called canonical forms, or resonance structures. These structures must have 1. Similar energy, 2. The same positions of atomic nuclei, 3. The same number of bonding and non-bonding electron pairs, just arranged differently. The actual structure of the molecule is considered to be a resonance hybrid of these canonical forms. It's like an average or blend of them.
So the real molecule is a mix of these drawings.
Yes, but it's not flipping between them. For or, we draw the two plausible Lewis structures, or OO, and connect them with a double-headed arrow. This signifies resonance. The resonance hybrid, sometimes drawn with dashed lines to show delocalized bonds, represents the true molecule where both OO bonds are identical and intermediate in character.
Are there other common examples?
Oh yes. The carbonate ion is another key example. You can draw three equivalent resonance structures, each with the double bond on a different oxygen atom. Experimentally, all three CO bonds in carbonate are identical in length and strength. The resonance hybrid shows the negative charge and double bond character distributed evenly over all three CO bonds. Carbon dioxide, CO arrow, also has resonance structures contributing to its overall description, though the OCO structure is the most significant.
What are the main takeaways about resonance? And are there common misconceptions students should definitely avoid?
Key takeaways. 1. Resonance leads to stabilization. The resonance hybrid is always more stable, lower in energy, than any single contributing canonical structure. This is called resonance energy. 2. Resonance averages bond characteristics. Bond lengths and strengths become intermediate between those expected for the single canonical forms. Crucial misconceptions to avoid. 1. Canonical forms are imaginary. They don't actually exist. Only the hybrid is real. They are just our way of representing the delocalized bonding on paper using familiar Lewis structures. Crucial misconceptions to avoid. 2. The molecule does not oscillate or flip rapidly between the canonical forms. It exists permanently as the hybrid structure. Crucial misconceptions to avoid. 3. There's no equilibrium between canonical forms. The double-headed arrow means resonance, not equilibrium. 4. The molecule has one single unique structure, the resonance hybrid. We just can't draw it perfectly with a single Lewis diagram. The zebra analogy you mentioned earlier is perfect. You can describe it using pictures of a white horse and the black horse. But the zebra itself is neither. It's something unique that blends those features.
That zebra analogy really sticks. Okay, moving on to polarity of bonds. You mentioned earlier that no bond is 100% ionic or 100% covalent. It's a spectrum.
Exactly. It's a continuum. Even in an ionic bond like NaCl, there's a tiny degree of electron sharing, covalent character. And even in a purely covalent bond between identical atoms like H, tiny fleeting temporary dipoles can arise. London dispersion forces. But generally, we classify bonds based on the sharing. Non-polar covalent bond formed between two identical atoms like HOBO-CLO. The shared electron pair is attracted equally by both nuclei and resides exactly midway between them. There's no permanent charge separation. Polar covalent bond formed between two different atoms with different electronegativities like HF, HCl, CO. The shared electron pair is pulled more towards the more electronegative atom.
Electronegativity is the key difference here.
Yes. This unequal sharing creates a separation of charge, resulting in partial charges. A partial positive charge, denoted plus, on the less electronegative atom, and a partial negative charge, denoted does, on the more electronegative atom. For example, in HF, it's H plus F.
And this charge separation leads to a dipole moment, right? Can you explain that?
Yes, precisely. This separation of positive and negative charge centers creates an electric dipole. The measure of this polarity is the dipole moment. It's defined as the product of the magnitude of the charge Q on either end and the distance separating the charges.
QAR.
Charge times distance.
Right. The unit is the Debye, named after Peter Debye. 1 Debye B E 3.33564, 10 aegis coulometers, cm. Dipole moment is a vector quantity, meaning it has both magnitude and direction. It's conventionally represented by a crossed arrow, pointing from the positive plus end towards the negative end. For HF, the arrow points towards F.
Okay, so that's for a single polar bond. What about molecules with multiple polar bonds, like water or Kyo-Euros?
Great question. For polyatomic molecules, the net dipole moment of the molecule depends not only on the individual bond dipoles, but also crucially on their spatial arrangement, the molecule's geometry. The overall dipole moment is the vector sum of all the individual bond moments.
Vector sum. So direction matters a lot.
Immensely. Let's look at examples. Water, H arrow. It has a bent shape. Angle 104.5 degrees. The two OH bond dipoles point towards the oxygen. Because of the bent structure, they don't cancel out. Their vector sum results in a significant net dipole moment, about 1.85 d. This polarity is why water is such a good solvent. Beryllium fluoride, BF arrows. VSEPR predicts it's linear, FBF. Each BF bond is polar, arrow towards F. But since the molecule is linear, the two equal bond dipoles point in exactly opposite directions. They perfectly cancel each other out, resulting in a zero net dipole moment. BFRs is nonpolar overall. Boron trifluoride, BFF. VSEPR predicts it's trigonal planar, 120-degree angles. Each BF bond is polar, arrow towards F. The three equal bond dipoles are symmetrically arranged at 120 degrees. Their vector sum is 0. So BF is also nonpolar overall.
So geometry can make a molecule with polar bonds nonpolar overall. That's important. Now, the classic comparison that always comes up in exams is NH years versus NF years. How does their geometry affect their dipole moments? They are both pyramidal, right?
Fantastic comparison, and yes, it's frequently tested. Both ammonia and nitrogen trifluoride, NF years, have a trigonal pyramidal shape due to the lone pair on the central nitrogen atom. Both have polar bonds, NH and NF.
So you might expect NF is to be more polar because F is more electronegative than H?
That's the common intuitive guess, but it's wrong. Experimentally, NF years has a significantly higher net dipole moment, about 1.47 d, than NF year, only about 0.23 d.
Wow, that's counterintuitive. Why?
It comes down to the direction of the bond dipoles and the contribution of the lone pair's orbital dipole. In NH years, the NH bond dipoles point towards the more electronegative nitrogen. The lone pair's orbital dipole also points away from the nitrogen atom in the same general direction as the resultant of the NH dipoles. So the bond dipoles and the lone pair dipole reinforce each other, leading to a large net dipole moment. In NHS, the NF bond dipoles point away from the nitrogen toward the highly electronegative fluorine atoms. However, the lone pair's orbital dipole still points away from the nitrogen atom in the opposite direction to the resultant of the NF bond dipoles. They partially cancel each other out, leading to a much smaller net dipole moment.
The lone pair direction relative to the bond dipoles makes all the difference. That's a brilliant explanation.
It really highlights how VSEPR shapes and vector addition are crucial for understanding molecular polarity.
So we've seen covalent bonds can have ionic character, polarity. Does the reverse also happen? Can ionic bonds have some degree of covalent character?
Yes, absolutely. As we said, it's a spectrum. Just as covalent bonds can be polar, partial ionic character, purely ionic bonds are an idealization. Real ionic bonds always possess some degree of covalent character due to polarization. This is described by Fajans rules.
Fajans rule, what do they say?
Fajans rules predict the extent of covalent character in an ionic bond based on the properties of the cation and anion. One size. A smaller cation and a larger anion lead to greater covalent character. Why? A small kappa cation has a high charge density, high polarizing power, and can distort the electron cloud of the anion more effectively. A large anion has a diffuse electron cloud that is easily distorted or polarized. 2. Charge. A greater charge on the kappa cation leads to greater covalent character. Higher charge means stronger attraction for the anion's electron cloud, increasing polarization. 3. Cation's electronic configuration. Cations with a pseudo-noble gas configuration, like N1 and S, typical of some transition metals like Cario, are more polarizing than cations with a true noble gas configuration, NS-Ampel, like Na or MdBu, of similar size and charge. The d electrons shield the nuclear charge less effectively, giving the cation greater polarizing power.
So the cations pulls the anion's electrons towards the space between them, making it a bit like sharing.
Exactly. The cation polarizes the anion, distorting its electron cloud and pulling some electron density into the region between the nuclei. This sharing of electron density introduces covalent character into the predominantly ionic bond.
Okay, that covers polarity and the ionic covalent spectrum. Now, we know the octet rule couldn't explain shapes, and dipole moments showed us geometry is vital. So how does VSEPR theory help us actually predict these shapes?
Excellent transition. The Lewis concept, as we established, fails on shapes. This is precisely where the valence shell electron pair repulsion, VSEPR theory, comes into its own. It's a relatively simple yet remarkably effective procedure for predicting the 3D shapes of covalent molecules, developed initially by Sidgwick and Powell and later refined by Nyholm and Gillespie.
Okay, VSEPR, what are its main ideas or postulates?
The core postulates are quite logical. 1. Shape depends on valence electron pairs. The overall shape of a molecule is determined by the total number of electron pairs, both bonding pairs and lone pairs, in the valence shell of the central atom. 2. Electron pairs repel. These electron pairs, being negatively charged clouds, repel each other electrostatically. 3. Minimize repulsion, maximize distance. To achieve maximal stability, these electron pairs arrange themselves in space in such a way that the repulsion between them is minimized, meaning they try to get as far apart as possible. 4. Valence shell as a sphere. Imagine the valence shell as a sphere, and the electron pairs position themselves on the surface of this sphere to maximize their separation. 5. Multiple bonds as single units. For VSEPR purposes, a double or triple bond is treated as a single superpair or a single electron domain. You count it as one region of electron density. 6. Resonance applies. The VSEPR model can be applied to any one of the valid resonance structures.
So it's all about electrons pushing each other away. Is there a specific order of how strong these repulsions are? That seems important for predicting the exact shape.
Yes, and this is absolutely critical for predicting the actual molecular shapes and understanding why angles deviate from ideal geometries. The order of repulsive interactions is lone pair, LP. Lone pair, LP. Bond pair.
Okay, bond pair, BP.
So lone pairs repel the most. Why is that?
The reasoning is that lone pairs are localized entirely on the central atom. They aren't shared between two atoms like bonding pairs. This means they occupy more angular space around the central atom. Because they take up more room, they exert a stronger repulsive force on neighboring electron pairs compared to bonding pairs.
Makes sense, they're fatter electron clouds. And this stronger repulsion causes distortions.
Precisely. These differences in repulsion strengths cause deviations from the idealized shapes, like perfect tetrahedral or trigonal planar, and lead to adjustments in bond angles. How do we actually use this to predict shapes? Can we walk through the process, especially comparing molecules with and without lone pairs?
Certainly. The prediction process involves counting the total number of electron domains, bonding pairs plus lone pairs, around the central atom and then considering the repulsion order.
Central atom with NO lone pairs. The molecular geometry is the same as the electron domain geometry. 2 electron domains, ABO type. Geometry is linear, 180 degrees. Examples: Bishuo-Okolo, 3 electron domains, ABO type. Geometry is trigonal planar, 120 degrees. Example: BFC, 4 electron domains, ABO type. Geometry is tetrahedral, 109.5 degrees. Example: CH, Sekilo, 5 electron domains, ABO type. Geometry is trigonal bipyramidal. Example: PCLO, 6 electron domains, AB type. Geometry is octahedral. Example: SFO.
Central atom with 1 or more lone pairs. This is where it gets interesting, and these are very common exam questions. The molecular shape, arrangement of atoms only, is different from the electron domain geometry, arrangement of all electron pairs.
Okay, let's see some examples here.
Let's take molecules based on 4 electron domains, like methane. Ammonia, type ABE, 3 bonding pairs, 1 lone pair. Total 4 domains, tetrahedral electron geometry, but the molecular shape is trigonal pyramidal. Why? The LPBP repulsion, BP, pushes the bonding pairs closer, reducing the H&H angle from 109.5 to about 107 degrees. Water, HH here. Type ABEU, 2 bonding pairs, 2 lone pairs. Total 4 domains, tetrahedral electron geometry. Molecular shape is bent or V-shaped. Why? Now you have LP repulsion strongest and LPBP repulsion. These push the bonding pairs even closer, reducing the HOH angle further to about 104.5 degrees.
So the number of lone pairs progressively squishes the bond angles. What about 5 electron domains? Good one. Base geometry is trigonal bipyramidal. Sulfur tetrafluoride, SF0, type ABE, 4BP, 1-LP. Electron geometry, trigonal bipyramidal. Where does the lone pair go? It prefers the equatorial position to minimize repulsions, fewer 90-degree interactions. This results in a seesaw molecular shape. Chlorine trifluoride, ClFeO, type ABO, 3BP2 heli. Electron geometry, trigonal bipyramidal. Both lone pairs go into equatorial positions to minimize repulsion. This leaves the atoms in a T-shaped molecular geometry. Xenon difluoride, XEOs, type ABO, 2BP3LSP. Electron geometry, trigonal bipyramidal. All 3 lone pairs occupy the equatorial positions. The 2 fluorine atoms are forced into the axial positions, resulting in a linear molecular shape.
And for 6 electron domains, base geometry is octahedral. Right. Bromine pentafluoride, BRFUs, type ABOE, 5BP, 1-PALP. Electron geometry, octahedral. The lone pair can go anywhere initially, but the resulting molecular shape is square pyramidal. Xenon tetrafluoride, XEOA, type ABO, 4BP, 2-PAL. Electron geometry equals octahedral. To minimize the strong LP-LP repulsion, the 2 lone pairs position themselves opposite each other, trans. This leaves the 4 fluorine atoms in a plane around the xenon, resulting in a square planar molecular shape.
Wow, VSEPR seems incredibly useful for predicting these shapes. Are there any limitations to it?
While VSEPR is remarkably successful and simple, its theoretical justification, especially regarding why lone pairs occupy more space, or the exact quantitative effects of repulsions, isn't rigorously derived from quantum mechanics. It's more of a highly effective empirical model. But for predicting shapes for exams, it's fantastic.
Okay, VSEPR gives us shapes based on repulsion. But it doesn't really explain why bonds form in the first place, or things like the difference in bond strength between H0 and F, even though both are single bonds. How does valence bond VB theory address this?
You've hit on the precise limitations that valence bond theory aims to overcome. Lewis doesn't explain how bonds form or bond energies. VSEPR explains geometry based on repulsion, but doesn't delve into the nature of the bond itself.
So VB theory goes deeper.
Yes. Valence bond theory, developed mainly by Heitler in London and significantly extended by Linus Pauling, provides a quantum mechanical description of bonding. It focuses on how atomic orbitals interact. Key concepts are atomic orbitals, their electron configurations, orbital overlap, and hybridization.
How does it explain bond formation, say, for the simplest molecule, H here?
Let's consider two hydrogen atoms, A and B, each with a nucleus, Na and B, and an electron, AAEB. Initially, when they're far apart, there's no interaction. As they approach each other, new forces come into play. Attractive forces. Nucleus Na attracts electron EB, and nucleus NB attracts electron EA. Also, the original NAEA and MBEB attractions, repulsive forces, between the two electrons, EAE, and between the two nuclei, Na and B.
A mix of push and pull.
Exactly. Experimentally and theoretically, it's found that as the atoms approach, the new attractive forces are stronger than the new repulsive forces initially. This causes the potential energy of the system to decrease, making it more stable.
So stability increases as they get closer.
Up to a point. The potential energy drops until it reaches a minimum value at a specific internuclear distance. At this distance, the attractive and repulsive forces are perfectly balanced. This minimum energy point corresponds to the formation of a stable H molecule. For H, this distance, the bond length, is 74 picometers.
And the energy drop is the bond energy.
Yes, the energy released when the bond forms, or the energy required to break it, is the bond enthalpy. For H0, it's 435.8 kilojmol. If you try to push the atoms closer than 74 pm, the nucleus and electron repulsions dominate rapidly, potential energy shoots up, and the molecule becomes unstable.
So this stable state at the energy minimum involves orbital overlap. What exactly is that?
Yes. The core idea in valence bond theory's explanation of covalent bonding is the orbital overlap concept. A covalent bond is formed when there is a partial interpenetration or overlapping of atomic orbitals belonging to the valence shells of the two participating atoms.
Orbitals merging slightly.
Right. This overlap allows electrons, which must have opposite spins according to the Pauli exclusion principle, to be shared between the two nuclei, effectively pairing up in the overlap region. The crucial principle here is the greater the extent of the overlap, the stronger the covalent bond formed.
More overlap, stronger bond. That seems intuitive. But you mentioned earlier that this simple overlap idea runs into trouble explaining the specific geometries in polyatomic molecules like methane, CH.
You're absolutely right to bring that up again. That's a critical point that leads directly to the need for hybridization. Simple overlap works well for diatomic molecules like HU or FU, but let's consider methane, CH.
Okay, CH. Carbon has 2s and 2p orbitals.
Carbon's ground state electron configuration is 2s7, 2pa. To form 4 bonds, we usually think of its excited state. 2PO, 2PAY10 might be 50 by A3, 2PAY10 might be 50 by A2PO. Now, if carbon used its 1, 2s, and 3, 2p orbitals to directly overlap with the 1s orbitals of 4 hydrogen atoms, what shape would you expect? The 3 orbitals, px, pi, pz, are mutually perpendicular, oriented at 90 degrees to each other.
So you'd expect some bonds at 90-degree angles.
Exactly. Simple overlap of these orbitals with hydrogen 1s orbitals would predict HCH bond angles of 90 degrees. But experimentally, we know methane is perfectly tetrahedral, with all HCH angles being 109.5 degrees. Simple overlap fails to explain this.
And similar issues for ammonia and water.
Yes. For NH and H0, if nitrogen and oxygen use their orbitals for bonding, we'd again predict bond angles around 90 degrees. But the actual angles are 107 degrees in NH and 104.5 degrees in H. This discrepancy clearly highlights the limitation of the simple orbital overlap picture and necessitates a more refined concept hybridization.
Okay, so hybridization is needed for shapes. Before we get to hybridization itself, could you briefly explain the types of orbital overlaps based on orientation? You mentioned sigma and pi bonds earlier.
Certainly. The way atomic orbitals overlap determines the type of covalent bond formed. For effective overlap leading to bond formation, the orbitals must have the same sign phase in the region of overlap. There are 2 main types based on the orientation of overlap relative to the internuclear axis, the imaginary line connecting the 2 nuclei. 1. Sigma bond. This type of bond is formed by end-to-end or head-on overlap of atomic orbitals along the internuclear axis. It's characterized by cylindrical symmetry around the bond axis. Sigma bonds can be formed by 1 sigma bond to overlap like an HES. So see 1 sigma bond to sigma bond to C end on overlap like an F bond. This type of bond is formed by the sidewise or lateral overlap of atomic orbitals. In this case, the axes of the overlapping orbitals remain parallel to each other but are perpendicular to the internuclear axis. This sidewise overlap results in electron density being concentrated in 2 regions. one above and one below the plane containing the internuclear axis. Pi bonds are typically formed by the sidewise overlap of p orbitals, pp's lateral overlap.
So sigma is head-on, pi is sideways. Which one is stronger?
The sigma bond is generally stronger than the pi bond. This is because the extent of overlap achieved in a head-on sigma fashion is significantly greater than the overlap achieved in a sidewise pi fashion. Greater overlap leads to a stronger, more stable bond.
That makes sense. And multiple bonds.
In molecules with multiple bonds, double or triple bonds, a double bond always consists of one sigma bond and one pi bond. A triple bond always consists of one sigma bond and two pi bonds. The sigma bond forms the fundamental framework connecting the atoms, and the pi bonds add to it.
Got it. Sigma first, then pi. Okay, so since simple overlap couldn't explain the geometries like the 109.5 degree angle in methane, is that where hybridization finally comes in as the solution?
Yes, absolutely. Hybridization is the brilliant concept introduced by Linus Pauling specifically to explain the observed characteristic geometrical shapes of polyatomic molecule shapes that simple overlap couldn't account for.
So what exactly is hybridization?
Hybridization is defined as the theoretical process of intermixing atomic orbitals of slightly different energies belonging to the same atom. This mixing redistributes their energy and shape to form a new set of equivalent orbitals called hybrid orbitals, which have identical energies and shapes.
Mixing atomic orbitals to get new identical hybrid ones.
Precisely. For example, in carbon, which needs to form 4 bonds in methane, instead of using 1,2s and 3,2p orbitals directly, these 4 atomic orbitals hybridize to form 4 brand new identical hybrid orbitals.
It's from 1 and 3p's.
Exactly. Here are the key features or salient features of hybridization. 1. Number conservation. The number of hybrid orbitals formed is always equal to the number of atomic orbitals that underwent hybridization. Usually 1s plus 3p equals 4 s-pion orbitals. 2. Equivalence. The hybrid orbitals formed are always equivalent in energy and shape. 3. Effectiveness. Hybrid orbitals are generally more effective in forming stable bonds than the original pure atomic orbitals because they allow for greater overlap. 4. Directionality and geometry. Hybrid orbitals are directed in specific orientations in space to minimize electron pair repulsion, just like in VSEPR theory. This specific orientation dictates the overall geometry of the molecule.
What are the conditions needed for hybridization to occur?
Good question. Some important conditions are: 1. Orbitals involved must belong to the valence shell of the atom. 2. The orbitals undergoing hybridization must have almost equal energy. E.g., 2s and 2p can hybridize, but 1s and 2p generally don't due to large energy difference. 3. Promotion of electrons, like from 2s to 2p in carbon, is not an essential prerequisite for hybridization itself, though it's often needed to explain the observed valency. For example, in NHOs and HO, the lone pairs are in hybrid orbitals without promotion. 4. Even filled orbitals in the valence shell can participate in hybridization if they have suitable energy. This is how lone pairs occupy hybrid orbitals.
Okay, let's dive into the common types of hybridization. sp, sp, and stellamimma. How do they lead to the linear, trigonal, planar, and tetrahedral shapes we talked about?
Absolutely. Understanding these 3 types is fundamental for class 11th JEE and NEAT sp hybridization. Orbitals involved. 1 s orbital plus 1 p orbital. Result. 2 equivalent is hybrid orbitals. Characteristics. Each orbital has 50% self-character and 50% p character. Geometry. The 2 support orbitals arrange themselves linearly, pointing in opposite directions to minimize repulsion. This results in a linear geometry with a bond angle of 180 degrees. It's sometimes called diagonal hybridization. Example: beryllium chloride, BSO. Beryllium's ground state is 1 s by 2 lessors. To form 2 bonds, 1,2's electron is promoted to a 2p orbital. Excited state, 1 source 2 sexual. Then the 1,2's and 1,2p orbital hybridize to form 2 sub hybrid orbitals. These point 180 degrees apart. Each pi orbital then overlaps axially, forming a sigma bond, with 2p orbital of a chlorine atom. Result: linear CLB LSBL molecule dot 2 s pi hybridization. Orbital as well. 1 spore plus 2 orbitals. Result: 3 equivalent spired hybrid orbitals. Characteristics: each powered orbital has roughly 33.3% psychocharacter and 66.7% psychocharacter. Geometry. The 3 spelt orbitals arrange themselves in a plane pointing toward the corners of an equilateral triangle. This results in a trigonal planar geometry with bond angles of 120 degrees. Example: boron trichloride. BCOS, boron's ground state is once the tidose 2s4 is ion one orbital electron is promoted, excited state. Once the sidose plus grows, then the 1,2's and 2p orbital hybridize to form 3 subpoddle hybrid orbitals. These lie in a plane at 120 degrees to each other. Each spotted hybrid orbital overlaps axially with a 2p orbital of chlorine, forming a sigma bond. Result: a trigonal planar BCOS molecule. The remaining unhybridized orbital on boron, if involved in pi bonding later, would be perpendicular to this plane. ECO hybridization. Orbitals involved: 1 s orbital plus 3 p orbitals. Result: 4 equivalent spot hybrid orbitals. Characteristics: each spore orbital has 25% spotter character and 75% back character in geometry. The 4 spore orbitals arrange themselves pointing towards the 4 corners of a regular tetrahedron. This results in bond angles of 109.5 degrees. Example: methane. CH. Carbon's excited state is the COS-NE2PO potency port anti-P by NE10 SP50 by A3 OPA Cinemax by 2 by pillow body and 2 by wires by P50 by A2 bit. The 1, 2s and 3, 2p orbitals hybridize to form 4 identical speedy hybrid orbitals. These are directed tetrahedrally. Each speedy hybrid orbital overlaps axially with the 1s orbital of a hydrogen atom, forming a CH sigma bond. This perfectly explains methane's tetrahedral shape and 109.5 degree bond angles.
That's clear for molecules where all hybrid orbitals form bonds. But how does Spock hybridization explain the distorted shapes we saw with VSEPR for ammonia and water and HOA, which have lone pairs? This connection is often tricky.
Excellent point, and this is where hybridization and VSEPR work together beautifully to explain reality. The key is that lone pairs also occupy hybrid orbitals and influence the geometry due to their stronger repulsive effect as per VSEPR. Example: ammonia, NHS. Nitrogen's valence configuration is 2,7,2 borders 2p0 by inni post-bill 50 by 2p0 by damn 2 and b50 by that 2 word. It undergoes SPI-SAPPHIRE hybridization, mixing its 2s and 2p orbitals to form 4 SPI hybrid orbitals arranged roughly tetrahedrally. Crucially, one of these SPI orbitals contains the lone pair of electrons, and the other 3 contain single electrons, which then overlap with hydrogen 1s orbitals to form the 3 NH2p bonds. Host speaker. So the lone pair sits in one of these SPI orbitals. Expert speaker. Exactly. Now, VSEPR tells us that lone pair bond pair LKVP repulsion is stronger than bond pair BPBP repulsion. This extra repulsion from the lone pair pushes the 3 NH bonding pairs slightly closer together, compressing the H-NH bond angle from the ideal tetrahedral 109.5 degrees down to about 107 degrees. The resulting molecular shape, arrangement of atoms, is trigonal pyramidal. Example: water H-air. Oxygen's valence configuration is 2 s-tons, 2p0 by 10 IB50 by A, 2po by 10 or IB50 by A2. It also undergoes small hybridization, forming 4 Squite hybrid orbitals arranged roughly tetrahedrally. Here, 2 of these orbital orbitals are occupied by lone pairs, and the other 2 contain single electrons which form the 2 OH sigma bonds. Host speaker. 2 lone pairs this time. Expert speaker. Right, now we have even stronger repulsions. Lone pair LP repulsion is the strongest, followed by LP-BP repulsion, then BP-BP. This combination of repulsions pushes the 2 OH bonding pairs even closer together than in ammonia. The HOH bond angle is reduced significantly from 109.5 degrees down to about 104.5 degrees. The resulting molecular shape is bent or angular or V-shaped.
That perfectly connects hybridization with the VSEPR distortions. Now, can we apply these Smovin and Spock's concepts to slightly larger organic molecules like ethane, ethene, and ethene, which involve carbon bonds?
Absolutely. Hybridization is fundamental to understanding the structure and bonding in organic chemistry. SPA hybridization in ethane, CROs. In ethane, both carbon atoms are SPI hybridized. SPI hybridization in ethane. 1 SPI hybrid orbital from each carbon overlaps axially with the other to form a strong CC sigma SPI hybridization. The remaining 3 SPI hybrid orbitals on each carbon overlap axially with the 1s orbitals of hydrogen atoms to form 6 CH sigma methane. All bond angles are approximately tetrahedral around 109.5 degrees. The CC single bond length is about 154 pm is SPI hybridization in ethene. Ethene, both carbon atoms are SPI hybridized. This SPI hybridization in ethene, each carbon forms 3 SPI hybrid orbitals, trigonal planar, 120 degrees, and has 1 unhybridized orbital perpendicular to this plane. Each SPI hybridization in ethene, 1 SPI orbital from each carbon overlaps axially to form a CC sigma ween. The other 2 SPI orbitals on each carbon overlaps axially with hydrogen Wiens orbitals to form 4 CH sigma. The other 2 SPI orbitals on each carbon overlap axially with hydrogen 1s orbitals to form 4 CH sigma. All these sigma bonds lie in the same plane. Now, the pi bond, the unhybridized p orbital on one carbon overlaps sidewise with the unhybridized p orbital on the other carbon above and below the plane of the sigma bonds. This forms 1 CC pi bond. Now, the pi bond, so the CCD double bond in ethene consists of 1 bond and 1 pi. The molecule is planar with HCH and HCC angles close to 120 degrees. The CP double bond length is shorter, about 134 pm S-key. Hybridization in ethene, ethylene and citrulline, both carbon atoms are spare hybridized. Each carbon forms 2 spare hybrid orbitals, linear 180 degrees, and has 2 unhybridized dihybridized p orbital, say pi and bz, perpendicular to the molecular axis, x-axis hybridization in ethene. One spin orbital from each carbon overlaps axially to form a cc sigma x-axis. The other spin orbital on each carbon overlaps axially with a hydrogen 1s orbital to form two CH sigma bonds. The HCCH framework is linear. Now the pi bonds, the pi orbital on one carbon overlaps sidewise with the pi orbital on the other carbon to form one pi bond. Similarly, the pk orbital on one carbon overlaps sidewise with the p orbital on the other carbon to form a second pi bond. Now the p bond, so the CIS triple bond in ethene consists of one bond and two bonds. The molecule is linear. The CI-She triple bond length is even shorter, about 120 pm.
That clarifies sigma and pi bonding in multiple bonds perfectly. What about elements beyond the second period? They can have expanded octets. Does hybridization involve d orbitals for them, like in PCl or SF?
Exactly. For elements in the third period and beyond, like PSCl, BRI, XC, vacant d orbitals in their valence shell, e.g. 3d, 4d, become energetically accessible and can participate in hybridization along with s and p orbitals. This allows for the formation of more than 4 bonds and explains the geometries associated with expanded octets.
So d orbitals join the mix?
Yes. Some important hybridization schemes involving d orbitals that you should be familiar with include DSPS. Leads to square planar geometry, often seen in coordination compounds like NiSOD or DSPO, leads to trigonal bipyramidal geometry, SF, CFO, CR, or DSPO, leads to octahedral geometry, e.g., SF, CRFO.
Sometimes shapes like square pyramidal BRE furos or T-shaped GCL furo arise from these underlying geometries when lone pairs are present, as VSEPR predicts. Let's look at 2 key examples. Formation of PCl eras, FT1 hybridization, phosphorus, PZ15, ground state config, Ne3 favors the 3p atomo. To form 5 bonds, 1,3's electron is promoted to an empty 3 orbit, giving the excited state. Ne3's PS3 at 3D metal. Hybridization. The 1,3's 3,3p and 1,3 orbital intermix to form 5 equivalent Zippy-Pod hybrid orbitals. Geometry. These 5 suitor orbitals are directed toward the corners of a trigonal bipyramidal. Bonding. Each sp hybrid orbital overlaps axially with a orbital of chlorine to form 5 PCl sigma bonds. Axial versus equatorial bonds. Important point. In the trigonal bipyramidal structure, the 5 positions are not equivalent. There are 3 equatorial positions in the triangular plane 120 degrees apart and 2 axial positions above and below the plane 90 degrees to the equatorial plane. Host speaker. So the bonds aren't all the same. X-Men speaker. Correct.
The axial bond pairs experience more repulsion from the 3 equatorial pairs at 90 degrees than the equatorial bond pairs, which have 2 neighbors at 90 degrees and 2 at 120 degrees. Consequently, the axial bonds are slightly longer and weaker than the equatorial bonds. This makes PCO0 quite reactive. It tends to lose the 2 axial chlorines easily. Formation of SF uros, sulfur SZ16, ground state config, Nethier 3p1. To form 6 bonds, 1,3's electron and 1,3p electron are promoted to 2 empty 3d orbitals, giving the excited state. Ne3CS3PO3D also. Hybridization. The 1,3's 3,3p and 2 3,2 orbitals intermix to form 6 equivalent pseudo-hybrid orbitals. Geometry. These 6 Bernoulli orbitals are directed towards the corners of a regular octahedron. All positions are equivalent, and all bond angles are 90 degrees or 180 degrees. Bonding. Each K4 hybrid orbital overlaps axially with the orbital of fluorine to form 6 equivalent SF sigma bonds. SF0 is a very stable and unreactive molecule due to the symmetrical structure and strong bonds.
Okay, VB theory with hybridization seems to explain shapes and bonding quite well. But you mentioned earlier it still has limitations, like explaining the magnetism of oxygen. Is that where molecular orbital MO theory comes in, providing an even deeper level of understanding?
You're absolutely right. Valence bond theory, while powerful in explaining shapes and localized bonds, struggles with certain molecular properties, particularly those involving delocalized electrons or magnetic behavior like the paramagnetism of oro. It also doesn't easily handle species like HA0. This is where molecular orbital MO theory, developed primarily by Hund and Mulliken, provides a more comprehensive and often more accurate picture, especially for diatomic molecules.
So MO theory is different from VB theory.
Yes, it takes a fundamentally different approach. Instead of visualizing bonds as localized overlaps between atomic orbitals, MO theory considers the molecule as a whole. Here are its key principles. These salient features. 1. Molecular orbitals, in those. Electrons in a molecule are not assigned to individual atomic orbitals, but occupy molecular orbitals that extend over the entire molecule, or large parts of it. 2. Formation from atomic orbitals, AOOs. Molecular orbitals are formed by the combination, specifically linear combination, of atomic orbitals of comparable energy and proper symmetry. 3. Polycentric. Unlike atomic orbitals, which are monocentric, centered on one nucleus, molecular orbitals are typically polycentric, influenced by 2 or more nuclei. 5. Conservation of orbitals. The total number of molecular orbitals formed always equals the total number of atomic orbitals combined. If you combine 2 AOs, you get 2 MOs. 5. Bonding and antibonding MOs. When 2 AOs combine, they form 2 MOs. One is a bonding molecular orbital, BMO, which is lower in energy and more stable than the original AOs. The other is an antibonding molecular orbital, MO, which is higher in energy and less stable than the original AOs. 6. Electron distribution. The shape and energy of MOs describe the probability distribution of electrons within the molecule. 7. Filling MOs. Electrons fill these molecular orbitals according to the same rules used for atomic orbitals. The Aufbau principle, fill lowest energy first. Pauli exclusion principle, max 2 electrons per orbital opposite spins. And Hund's rule, fill degenerate orbitals singly first before pairing.
Okay, so electrons belong to the whole molecule in MOs. How are these MOs actually formed? You mentioned linear combination of atomic orbitals, LCAO.
Yes, LCAO is the mathematical approximation used to describe the formation of MOs. We think of atomic orbitals as wave functions. Let's take the simplest case, forming H from 2 hydrogen atoms, A and B, each with a 1's atomic orbital. Wave functions Ben and BEMIC. According to LCAO, these 2 AOs can combine in 2 ways. Addition, constructive interference. CBO equals A plus PIM. When the wave functions add up constructively, electron density increases in the region between the 2 nuclei. This increased density shields the nuclei from each other, reduces repulsion, and pulls the nuclei together, resulting in a stable bonding molecular orbital. We call this M, sigma bonding from valence orbitals. It's lower in energy. Subtraction, destructive interference. CABMO CPO. When the wave functions subtract, combine out of phase, electron density cancels out in the region between the nuclei, creating a nodal plane, a plane with 0 electron density there. The electron density is pushed outside the internuclear region. This increases repulsion between the nuclei, destabilizing the molecule, resulting in an antibonding molecular orbital. We call this SUNS, sigma antibonding, from one's orbitals. The asterisk denotes antibonding. It's higher in energy.
So adding waves makes a stable bonding MO, subtracting makes an unstable antibonding MO. What are the conditions for atomic orbitals to combine effectively?
Good question. For effective combination via LCAO, 1. Comparable energy. The combining atomic orbitals must have similar energies. For example, a 1s orbital will combine effectively with another 1s orbital, but not very effectively with a 2s orbital because their energy difference is too large. This is especially true for homonuclear diatomics. 2. Proper symmetry. The combining atomic orbitals must have the same symmetry with respect to the molecular axis, usually defined as the z-axis. For instance, a 2ps orbital on one atom can combine with a 2ps on another, head-on overlap to form some O's. However, a 2ps cannot combine effectively with a 2px or 2pa orbital because their symmetries don't match along the internuclear axis. A 2px can combine with a 2px sideways overlap for 2pos. 3. Maximum overlap. The extent of overlap between the atomic orbitals must be significant. Greater overlap leads to stronger bonding, lower energy BMO, and stronger antibonding, higher energy ABO. Okay, energy, symmetry, and overlap. What types of MEOs are formed? We saw SFA from s orbitals. What about p orbitals?
P orbitals lead to both sigma and pi molecular orbitals. SIGs, these are formed from the head-on overlap of orbitals along the internuclear axis, z-axis by convention. This can happen with sigma motul sabi overlap, sigma overlap. Sigma motils are symmetrical around the bond axis, pi moos. These are formed from the sideways overlap of p orbitals, px with px or pi with pi, that are perpendicular to the internuclear axis. Pi, px, px, overlap pi mos, that are perpendicular to the internuclear axis. Pi mopolimispos, pi px overlap, pi amorosibros, pi overlap, pi mos, piomos. Pi mos are not symmetrical around the bond axis. They have electron density above and below it, with a nodal plane along the axis itself. The bonding PAMO has density concentrated between the nuclei, above-below axis, while the antibonding PAMO has an additional node between the nuclei. Got it.
Sigma from head-on, pi from sideways. Now, the really crucial part for exams, the energy level diagram for these MOs. You mentioned earlier there are 2 different orders. That sounds like a common trap.
It is. You absolutely must know which energy order to use for which molecules. The relative energies are determined experimentally and via complex calculations. But for diatomic molecules of second period elements, Lyo to Nero, there are 2 observed sequences for filling the MOs derived from the 2s and 2p atomic orbitals.
Observed for oberos and euros, the increasing order of energy is?
The increasing order of energy is Swiss px, 2px, 2px.
Orbitals are degenerate, same energy.
Mm-hmm.
In this case, the 2ts is lower in energy than the 2px and 2p.
Observed for loose deuterous B, V, C, and N rows, the increasing order of energy is Sons 1 so Phi so PX2 P to PX2 PS. The key difference is right here. For B, C dosen, the 2px and 2pSOs are lower energy than the 2ps MO. This reversal is attributed to the mixing between 2s and 2ps orbitals, which is significant for the earlier elements in the period, but less so for O and F.
Okay, so remember P below for B, C ends N, and so P is below for O or OS. Got it. Once we have the correct energy order and fill in the electrons, how do we use this MO configuration to predict the molecule's behavior, like stability, bond order, magnetism?
This is where the power of MO theory becomes really apparent. Once you have the MO electronic configuration you want for Na uso, you can determine several key properties. 1. Stability of the molecule. Count the total number of electrons in bonding MOs. NB. Those without an asterisk. 7s, 2px, 2p. Count the total number of electrons in antibonding MOs, just those with an asterisk. Swins, solis, 2kx, 2px, 2ps. Count the total number of electrons in antibonding MOs. No, those with an asterisk. The molecule is predicted to be stable if NB no. Bonding electrons stabilize, antibonding electrons destabilize. Count the total number of electrons in antibonding MOs. Nay, those with an asterisk. The molecule is predicted to be unstable and likely won't form if NB, NB, nay. 2. Bond order, BO. This gives a quantitative measure of the net number of bonds. Formula, BO, accession, NB, Fe, formula. A positive BO, meaning NB nay, indicates a stable molecule. Higher bond order generally means a stronger, shorter bond. Formula. A BO of 1, 2, or 3 corresponds to a single, double, or triple bond, respectively, in line with Lewis theory. Formula. A BO of 0 or negative indicates an unstable molecule. 3. Magnetic nature. Major advantage of MO theory. This is crucial. 3. Magnetic nature, major advantage of MO theory. Examine the filled MO diagram. If all molecular orbitals are doubly occupied, i.e. all electrons are paired, the substance is predicted to be diamagnetic, weakly repelled by a magnetic field. 3. Magnetic nature, major advantage of MO theory. If one or more molecular orbitals are singly occupied, i.e. there are unpaired electrons, the substance is predicted to be paramagnetic, attracted by a magnetic field. MO theory is excellent at predicting this.
Okay, let's apply this systematically to a few classic homonuclear diatomic examples that always seem to come up, like why doesn't helium form HERO? And especially, let's reconfirm why UO is paramagnetic using MO theory.
Excellent choices. These illustrate the principles perfectly. 1. Hydrogen molecule, H. 1 hydrogen molecule, H. Total electrons 1 plus 1 equals 2. Energy order simple. Slit configuration NB equals 2 little limo. Configuration bond order equal 3 little limo. Product Watts 1. Predicts a stable single bond. Magnetic nature. All electrons paired. Predicts diamagnetic. This matches reality. H resists, has a single bond, and is diamagnetic. 2. Helium molecule. Total electrons 2 plus 2 plus 4. Energy order. Configuration NB2, no up 2. Configuration bond order have 2, there level. Conclusion. A bond order of 0 means the molecule is unstable and should not exist. This perfectly explains why helium exists as individual atoms, monatomic gas. The stabilization from the bonding electrons is completely canceled by the destabilization from the antibonding electrons. The same logic applies to B, it also has BO0 and doesn't exist. 3. Lithium molecule, LiO. 3 lithium molecule lighter. Total electrons 3 plus 3 plus 3 aqueous. Energy order, use the 1 for early elements. Configuration. We can abbreviate the core electrons as KK, so configuration. NBS2 from C plus 4, no S2 from C is configuration. Bond order half 4 2, if at least 1, predicts a stable single bond. Magnetic nature, all electrons paired. Predicts diamagnetic. Result. Lyase is known to exist in the vapor phase and is stable. 4. Carbon molecule, C. Total electrons 6 plus 6 equals 12. Energy order, crucial relative to 4 C's, NB, NBPX2, OPX25. Note we fill 2px and 2px, C's low force MB, MBPX, 2px, PPX, note which fill 2px and 2px, CO. Note we fill 2px and 2px for or left before. Note we fill 2px and 2px, 2pcs predicts, 2px, 2ppx, integer%. Bond order predicts a stable double bond. Magnetic nature. The last electrons fill 2px and 2p completely paired, predicts diamagnetic. Interesting insight. MO theory reveals that the double bond in C consists entirely of 2 pi bonds because the orbitals are filled before the host 2 pairs. This is unusual. 5. Oxygen molecule. 5. Oxygen molecule. O. Total electrons equals 8 plus 8 plus 8 equals 16. Energy order. Crucial. Order 1. Pay attention to the very last part. According to Hund's rule, the last 2 electrons go into the degenerate orbital singly with parallel spins. Configuration NB 1 plus 2 pieces plus 4 equals 8 valence or 10 total, and that 2 plus 2 plus 2 plus 2 equals 6 total. Configuration: bond order half 10 6 on Lewis 2 predicts a stable double bond consistent with Lewis. Magnetic nature: because there are two unpaired electrons, one in 2px, one in 2p, MO theory correctly predicts that O is paramagnetic. This is a major success story for MO theory, explaining experimental observations where simpler theories failed.
Wow, MO theory really is powerful, especially for explaining magnetism and giving those bond orders. Okay, we've covered ionic, covalent, Lewis, VB, MO. What about that other important interaction, hydrogen bonding? It comes up a lot in biology and chemistry.
Excellent point to conclude with. Hydrogen bonding isn't a formal covalent or ionic bond within a molecule, but rather a special, relatively strong type of intermolecular force, an attraction between molecules. It plays a crucial role in determining the properties of many substances, especially water, ammonia, HF, and biological molecules like proteins and DNA.
So it's an attraction between molecules. How is it defined?
A hydrogen bond is defined as the attractive force between a partially positively charged hydrogen atom, which must be covalently bonded to a highly electronegative atom like fluorine, F, oxygen, O, or nitrogen, N, in one molecule, and a lone pair of electrons on a highly electronegative atom, again, usually F, O, or N, of another molecule, or sometimes within the same large molecule.
So H bonded to F over N is key.
Yes, that's the prerequisite. It's usually represented by a dotted line to distinguish it from a full covalent bond solid line. For example, H2 plus X to R, where X and Y are F, O, or N, the hydrogen acts like a bridge between two electronegative atoms.
What causes this attraction to form? Why specifically FON?
It arises directly from bond polarity. When hydrogen is covalently bonded to a very electronegative atom, F, O, or N have high electronegativity values, the bonding electron pair is pulled strongly towards that electronegative atom,
Creating O plus on H and on FON?
Exactly. This leaves the hydrogen atom with a significant partial positive charge, making it almost like a bare proton in extreme cases. The electronegative atom gains a significant partial negative charge and usually has lone pairs of electrons. The electrostatic attraction between the S plus hydrogen of one molecule and the O lone pair region of the F, O, or N atom on an adjacent molecule constitutes the hydrogen bond.
So it's an electrostatic attraction between polar molecules.
Essentially, yes, but it's stronger and more directional than typical dipole interactions. Its strength depends on the electronegativity difference and the physical state, strongest in solids, weakest in gases. Hydrogen bonding is responsible for many anomalous properties, like the unusually high boiling point of water compared to H arrows, etc.
Are there different types of hydrogen bonds?
Yes, broadly two types. One, intermolecular hydrogen bond. This is the most common type, formed between two separate molecules. These can be molecules of the same compound, for example, between water molecules leading to its extensive 3D network, between HF molecules, between alcohol molecules, or between molecules of different compounds, for example, between water and ammonia or water and alcohol. Two, intramolecular hydrogen bond. This type forms within the same molecule. This occurs when a hydrogen atom, bonded to F, O, or N, is positioned such that it can form an attractive interaction with another electronegative atom, F, O, or N, within that same molecule, often forming a stable ring structure. A classic example is O-nitrophenol, where the hydrogen of the OH group forms a hydrogen bond with one of the oxygens of the adjacent ecano group on the same benzene ring.
Inter between molecules, intros within a molecule. Got it. That seems to cover the major types of bonding and interactions we needed to discuss.
Indeed. So let's quickly recap this deep dive into chemical bonding and molecular structure. We started with the foundational Kössel-Lewis approach, understanding the drive for the octet and the basic concepts of ionic electron transfer and covalent electron sharing bonds. We learned the systematic way to draw Lewis dot structures and the utility of formal charges in evaluating them.
And critically, the limitations of the octet rule, incomplete octets, odd electron molecules, and expanded octets.
Exactly. We then explored the stability of ionic compounds, realizing that lattice enthalpy is the key stabilizing factor. We quantified bonds using parameters like bond length, bond angle, bond enthalpy, and bond order. The crucial concept of resonance helped us accurately represent molecules like ozone and carbonate, where single Lewis structures fail.
We also covered bond polarity, dipole moments, and how molecular geometry, predicted by VSEPR theory, dictates the overall molecular polarity, using examples like water, Kuros, and the NHE-NFE comparison. Fajon's rules explain the covalent character in ionic bonds, too.
Then, VSEPR theory itself gave us a powerful tool to predict molecular shapes based on minimizing electron pair repulsion, explaining deviations due to lone pairs. We stepped up to valence bond theory, describing bond formation via orbital overlap, sigma and pi bonds, and introducing hybridization, SFU, SP speed A, to finally explain the observed molecular geometries accurately.
And finally, the more advanced molecular orbital theory, which provided a delocalized view, correctly predicted properties like bond order, and importantly, magnetism, explaining OA's paramagnetism, offering perhaps the most complete picture for diatomic molecules.
And we wrapped up with the vital concept of hydrogen bonding, distinguishing between its intermolecular and intramolecular forms, and acknowledging its profound impact on the properties of many important substances.
Wow, that was an incredibly thorough deep dive. It really clarified how these theories connect and build upon each other, giving us progressively deeper understanding. Breaking it down like this is so helpful for tackling exam questions. This detailed approach is absolutely invaluable for cracking those competitive exams like JG and NEET.
Absolutely. And for all of you listening, remember, the key to mastering chemical bonding and molecular structure for your Class 11th boards, JE or NEET, is not just memorizing definitions. It's about truly understanding the why and how behind each theory and concept. Why does resonance occur? How does hybridization explain shape? Why is MO theory needed for magnetism?
That makes sense. Focus on the concepts.
Definitely. Make sure you revise all these topics thoroughly. Pay special attention to the exceptions to the octet rule, the application of VSEPR theory to different ABRO by 10sb50 by A7 types, and the unique insights from MO theory, especially the energy level diagrams and predicting properties.
Practice is key too, right?
Immensely. Practice drawing Lewis structures until it's second nature. Get comfortable predicting shapes using VSEPR for various molecules and ions. Practice calculating bond order and determining magnetic nature using MO theory. And most importantly, solve as many past year questions based on this chapter as you possibly can. That's where you'll really solidify your understanding and build confidence for the exams.
Great advice.
And if any doubts remain on this crucial chapter, please don't hesitate to reach out for further clarification. Keep learning, keep exploring the fascinating world of chemistry, and all the very best for your exams.